Okay. All right. Well, thank you very much. Is everything working?
Yeah, our second speaker is Professor Zhang from Harvard University. So talking about the cuprate.
Okay. Well, thank you very much, Naoto. It's a great pleasure to have you all here from Kyoto and Tokyo. Really enjoying the meeting, and thank you for inviting me. Okay, so this is about the cuprate superconductors, and an old topic, and not so far discussed, but still behind many of the deep questions that many of you are addressing. But I want to focus here on actually a very recent observation of the Yamaji, and how I believe it's giving us a lot of new insight into a very old problem. So anyway, quick reminder. So this is the high temperature superconductor, YBCO, and this is the parent insulator, which is just a square lattice of copper atoms. And in the insulator, there's long-range antiferromagnetic order with 1 electron per site. And then when you dope the system with the whole density P, you get high temperature superconductivity. So this is the doping density. The density of electrons here is 1, or holes is 1 at this point. And then when you dope it, the total number of holes with respect to the fill band of the copper sites is 1 plus P. All right, so I'm not going to go into the details of this phase diagram. It's taken 30 plus years to unravel all this complexity. Of course, notice the very notable feature that TC is very high and still the highest among any material at ambient pressure, and in a material that you can hold in your hand and build things from. Okay, but let's go to the high doping regime where things seem to be extremely well understood. So here in the high doping regime, you can just imagine you have free electrons. So the total density, I'll speak in terms of holes, the density of holes with respect to the fill band, as you would count in a semiconductor, is 1 plus P. And that's exactly what you see in photoemission. This is the Fermi surface, the boundary between occupied and unoccupied states. And if you look at the area of this region here, it's exactly 1 plus P. And that is a verification of a fundamental theorem of solid-state physics, the Luttinger theorem from 1960, that the area enclosed by the Fermi surface is the same as that of free fermions, that interactions don't renormalize the area. Correspondingly, if you measure the Hall effect, which is another way to measure the density of mobile carriers, you get the Hall effect just as expected of 1 plus P. The reason you don't see 1 minus P, why don't you see and think in terms of electrons? You want to think in terms of holes, because the Fermi surface is circular, a simple circle. When you think in terms of holes, it has a negative curvature in terms of electrons. So it's really more efficient to think in terms of holes, and that immediately gives you the right Hall coefficient. Okay, but my focus here on the low doping regime, the so-called pseudogap regime. Oh, sorry, before I go there, there's a modern view of this deep theorem due to Oshikawa, and an even more, which is in 2000. And today we'd say that Oshikawa's result is an anomaly argument. There's a certain anomaly associated with translations and charge conservation, which you can formulate in terms of inserting flux of the system placed on a torus. And there's a certain anomaly in the theory, which is just the density of holes or electrons. And then you derive the Luttinger theorem by assuming that the low energy excitations only have a Fermi surface. And then you compute the anomaly for the Fermi surface, and the equality of the two anomalies gives you back the Luttinger theorem. So this is really a much simpler and much more beautiful argument. To understand Luttinger's argument, you have to pages and pages of Green's functions that don't give you much physical insight. All right, so now moving to the low doping regime. So here, the first fact is that if you look at the Hall coefficient, the simplest way to measure the density of carriers, you get holes of density P, not 1 plus P. You get a very different Hall coefficient. So this means that how can we understand P? Well, in the simplest manner, is simply you have an insulator here, and you just imagine that the insulator electrons don't move, and then the dopant holes from the insulator, which was the antiferromagnet, I mean, to remind you, this is an insulator only because of strong interactions. For free fermions, P equals 0 would be a metal. So you imagine that interaction in your insulator is there, and then the dopants are the carriers that are moving, so you get holes with density P. All right, so that already, raises a lot of puzzles. What does the Fermi surface look like? Well, it looks rather of a mess, something called the Fermi arc spectrum. But I'll return to that towards the end of my talk, if there's time. Okay, and we'll explain the whole spectrum and also a lot of the phenomena by something called Ethel star. And let's see, I probably won't have time to go into the details of that. But let me jump ahead to literally a couple of weeks ago from experiments that were 20, 25 years old. And there's something called the Yamaji effect. Perhaps some of you know Professor Yamaji. I had never heard of the Yamaji effect way back in 1989. This was discovered in the study of another class of quasi two-dimensional materials, the organic superconductors. And the effect was the following. It's very beautiful. Imagine you have some two-dimensional Fermi surface here, but the layers are coupled. And because of the coupling, the Fermi surface is not independent of the z direction. It has a gentle cosine warping, very small warping. Okay, this is due to the tunneling between the layers. And this particular experiment that I'm reporting here is in this compound where the coupling between the layers is very simple, just simple AA stacking of the square lattices. So again, you get this cosine band. Now, what Yamaji pointed out was that if you apply a magnetic field at some angle theta and measure the resistance in this direction. Okay. So what do you point? So now, semi-classically, you expect the electrons to undergo this orbit. And the area of the orbit is what determines the dispersion in the z direction. So what Yamaji pointed out that the area of this orbit is actually independent of kz to first order in the warping at a very special angle that we now call the Yamaji angle. And in fact, there's a simple formula for the Yamaji angle relating the c-axis spacing and the area of the Fermi surface. So if you see the Yamaji angle, you have a clean measurement of the area of the Fermi surface. Okay. So that's what, so people have been, I had never heard of it. People of the more familiar way to look at Fermi surface is quantum oscillations at very low temperatures, where you see oscillation of resistivity for motion in this direction. And that's been observed, but down at very low temperatures. But if you remember from the phase diagram, lots of other things happen at low temperatures and high fields, including charge density wave order and so on. So that messes up what the actual state of the electrons is before they become superconductor. So the early Fermi surface probe so far has been, in fact, this is one of the best, by far the best probe of the Fermi surface. So here's the actual data, just published a couple of weeks ago. There's the peak. This is the theta Yamaji. And from this, they are able to read off the size of they assume there are 4 pockets like this. And the total density of carriers is P, because we know from the Hall effect that the density of carriers is P. And assuming these elliptical pockets, they can actually compute the entire theta dependence in a Boltzmann approach of the c-axis resistivity. And this is the main conclusion in their paper, that there are small pockets in this region with the area approximately 1.3% of the Brillouin zone at the doping of P equals 0.1. And at least in this paper, they leave open, what is this 1.3%? I'm sure they have a pretty good idea, but okay. All right, so we want to understand that 1.3%, and I'm going to argue that actually it was predicted. So we have to start here from the Mott insulator, which is an antiferromagnet, and dope it and ask what is the natural metallic state you'd obtain for this process. Okay, first, as I've already mentioned, if you go to very high doping, you don't start from a Mott insulator, you start from a band insulator. then the number of holes is 1 plus p. And after accounting for a factor of 2 for spin, the area of this region, and the fraction in units where the area of the square is 1, the area of the green region is 1 plus p over 2. That's where the holes are. All right, well, we want to start from an insulator. So this is the insulating antiferromagnet. And now you put in a few holes. And these become mobile, and maybe you get a metallic state, but you still have long range order. So in this case, the symmetry has been broken. But you can ask from the Luttinger argument, in the presence of the broken symmetry, what is the Luttinger prediction for the size of the Fermi surface? So that's a relatively simple calculation. And the answer is you get 4 pockets with the area P over 4. Now, why is that P over 4? So it's a somewhat subtle argument. Because you have a broken symmetry, your Brillouin zone is this diamond, this dashed blue line. So really you only have 2 pockets. These two are just related by reciprocal lattice vector with the new symmetry. But you have 2 pockets and a factor of 2 for spin. And hence, since the total density of holes is P, the area is P over 4. 2 for spin and 2 for valley. Okay, so that's the prediction of an antiferromagnetic metal. And in fact, there's some very beautiful experiment by Professor Kondo, which have actually verified this P over 4 for antiferromagnetically ordered phases in multi-layer visco compounds. Okay, but how about a more exotic state where you don't have any broken symmetry? Because the trouble with this explanation, as we know, is essentially no magnetism at these doping and temperatures. So then the suggestion is you think in terms of some spin liquid, an RBB types. This is a very simple cartoon of such a state. I think Amelia Kobe drew some pictures yesterday. So here you have an RBB state with resonating valence bonds, and you put in a few holes. And then the holes can move. So these objects that are moving now don't carry any spin, as you can see from this picture. It's only the charge is moving. So these are spinless particles with charge E. So that's what we call them holons. And if these are fermions, as they are in some models, they form a Fermi surface. You can still apply, and that's the important point, the Yoshikawa argument to this state. You can't apply the Luttinger argument because this state is not, in fact, it gives you the wrong answer because there's no broken symmetry. So Luttinger would say in this state that you have a large Fermi surface, which you don't. And the reason you don't, because this is a non-perturbative state with a spin liquid. And what we argued in these papers was that you can then satisfy the Yoshikawa anomaly by 2 different contributions. One from the spin liquid, which in this case is 1, and then the Fermi surface of these holons, whatever they may be, which density is P. So from that, you then see that you can get pockets of whose total area must be P. And now in this case, if you in many simple calculations, you get 4 pockets again. But the Brillouin zone is not halved. So there are 4 pockets. These are spinless particles. So in this case, somewhat unfortunately or fortunately, the area is again P over 4. But for very different reasons. It's a factor of 4 from valley. There's no factor of 2 from spin. All right, so this is another possible state, but just measuring the Fermi surface will not distinguish it from the antiferromagnetic metal, at least in quantum oscillations. These are spinless particles. So if you're doing photo emission, you will see an immediate difference. Okay, however, there's another state I want you to consider. Now, this is a spin liquid. The holon metal also has spin-on excitations that Amir mentioned yesterday. These are spin-fold neutral particles. And now you can imagine a situation where every holon traps a spin-on. Maybe there's some attractive interactions in them. And they can form a bound state represented by these green dimers. So each green dimer is just an electron, if you wish, hopping back and forth between these 2 sites. So it's a very simple, strong coupling picture. And now you can also see from this very simple picture why the bound state may want to form. When you create a spin-on, you have to pay some energy to create these spin-ons. That energy is about a J. On the other hand, when you form a bound state, then this state here has the electron hopping back and forth, you get energy over a T. So in fact, as long as T is bigger than J, you will always form these bound states. So now you have a spin liquid state. The spin liquid is still there, but the mobile carriers carry both spin and charge. So they're just like an electron or a hole. They spin charge plus E relative to the Mott insulator and spin a half. And these can move around. And they're necessarily fermions in any theory. And they can form a Fermi surface. So if you do some calculations of this, you're going to get 4 pockets. But now you have 4 valleys, and you have a degeneracy of 2 from spin. So that gives you area P over 8. Okay, so that's to summarize. There are 3 possible states I've talked about. One is the antiferromagnet, which has area P over 4. And if you thermally fluctuate this, you can still get P over 4. The other is the hole-on metal, which still has P over 4. And this has P over 8. Now, of course, I presented this in very simple arguments, just in these cartoon wave functions. That's all you need to understand the numbers. But they're very robust. So this is, the nice thing about having anomalies and all of that is that we get to enjoy some of the beautiful features of the quantum Hall effect. Certain things are quantized. And these things are quantized. These numbers are quantized, P over 4, P over 4, and P over 8. And even much more complicated states, which are surely needed to describe the real situation, will have the same value. Okay. All right. And I just want to mention this paper way back in 2007, where we explicitly wrote down this delta over 8, which is different from the nail state or the hole-on metal states. Anyway, okay, so what works? Well, doping is P of 0.1, and P over 8 is 1.25%. So quite close to what's been observed. So we are very happy. I should also mention there are various somewhat earlier works by Yang, Rice, and Zhang. I mentioned they didn't say this explicitly, but implicitly they're talking about P over 8, and also in various other experiments and theories. But anyway, the quantization and the requirement of this P over 8 was discussed by us. All right, so of course this needs more experiments. We need more dopings, and maybe someday people will see quantum oscillations of these pockets. We don't know. Okay, so that's the main point I wanted to get across. All right. How am I doing on time?
You have 12 minutes.
Oh, okay, good. So that's the latest experiment, and I argue that if this explanation holds up that I'm presenting, it's certainly true that this is the best evidence yet for fractionalization to cuprates. I'm not saying it's conclusive evidence or anything. It's better than all previous evidence. That's the careful statement that I think is valid here. And yeah, I'm certainly believe this is fairly good, and this is the correct way to think about things, but let's see. All right, so what about everything else? I just talked about the Yamaji effect. What about photoemission, where you don't see a pocket? Why is that? So for that, it turns out, in this, if you look at this picture here, I was talking all about the motion of the green objects. The green objects move around, those are the holes, and they form these Fermi pockets. I just treated them as free particles. But there's also the blue object, there's a spin liquid sitting there. And I just completely ignored it. Now, for the purposes of the Fermi surface area, that's valid, because the anomaly argument doesn't care what particular type of spin liquid you have. But if you want to compute photoemission or anything else, you do have to worry about it, okay? So then you can, then what about the spin liquid? So now, of course, the idea of a spin liquid goes back to Anderson and Bhaskaran. And that was in 1987 when there was no theory of spin liquids. Today, we have theories of lots of spin liquids. There's whole tables of them. They're classified on different lattices. And so now, if I'm going to apply spin liquid theory to cuprates, so immediately the question is, which spin liquid? Tell me which one. Okay, I will. So this is work with various people. My student Maine, who is now at Caltech, and Alex Nikolenko, who was a student here, and Pietro Bonetti, who was also a postdoc here, in a collaboration with people in Chennai. And here's a review article with my former title, with Avishkar Patel on all of these topics that I invite you to look at if you want to know more. All right, so here's the spin liquid that I believe, for various reasons, is the correct one. And when this spin liquid was proposed in some form already in this remarkable paper of Affleck and Marston in 1988. And a lot of work's been done in the nearly 40 years since then. And in particular, there's this very beautiful work by Yin-Chen He on the fuzzy sphere just a few years ago, which has really given very convincing evidence that on the square lattice, this spin liquid of Affleck and Marston is pretty much there. But it's unstable at very long distances, but over a very substantial length scale, it is the correct way to describe spin correlations in the square lattice antiferromagnet, as it's losing its long range order. For now, all I will tell you is what the low energy theory of the spin liquid looks like. Well, the low energy theory has Dirac cones. This is just like graphene. Graphene also has Dirac cones, but in graphene, the Dirac cones are of electrons, which carry spin and charge. In this case, these Dirac cones are of spin-ons, which carry spin. They're also fermions, but no charge. So you can't just do a photo emission and see that, like as you can see in graphene. They're much more subtle because they don't carry charge, and you can't remove them from the sample. Anyway, and also because they're fractionalized particles, they must couple to a gauge field. And what we know now is that the correct description is to take two flavors of these Dirac massless spin-ons, couple them to an SU2 gauge theory in group of one dimension. And a curious fact is very, very similar to quantum chromodynamics, except you change all the 2's to a 3 for the light quarks. Okay. Anyway, so this is the theory, the spin liquid that we want to work with. And largely due to the convincing, there's a lot of numerical work, including by Professor Imada in Japan. And I think that all leads to the conclusion, especially this last work, that this is the correct spin liquid. Okay, so now I've told you about this FF star theory for the pockets. You have to couple the FF pockets to this particular spin liquid. So that's the technical issue that theorists have been struggling with for 25 years. How do you dope a spin liquid, and in particular your favorite spin liquid? And in fact, you have to dope it not to holons, but to electrons or holes. So here there's been a technical development which I found very powerful. It's something we call the ancillary layer model, an idea due to Yamaji Zhang. And that, I don't have time to go through that. So there's a way to write this down where you take the theory of the pockets, and then you couple it to these Dirac spin-ons, which are sitting at these 4 points. And the coupling goes via Higgs field and it's SU2 gauge theory. So it's a very difficult theory to simulate. However, we're interested in the finite temperature behavior. So we made the assumption that we can just do a thermal average over the gauge fluctuations. So the fermions are accounted for quantum mechanically, but all the bosons, the gauge field and the Higgs fields, are just average over thermally in the Monte Carlo study. And when you do that, you get Fermi arcs. This is in this recent paper with Monte Carlo done in Chennai by the lattice gauge theory group. And you get, the Fermi arcs just as you, quite similar to what you saw in the experiment. And this happens because basically the backside of these pockets couple very strongly to the spin-ons. And that basically reduces the spectral wave on the backside and washes it out while giving you these arcs. Okay. Now you might wonder, well, this is very dangerous because wouldn't this destroy the Yamaji effect? Because you've destroyed the backside. All right, so that's also, we haven't computed the Yamaji effect, but we looked at quantum oscillations. So we took this gauge theory and tried to see if it had any signal of the quantum oscillations still around. So that's this plot here. So this is a simplified version of the gauge theory. You have to do it in a really rather big samples. We're talking about fairly small pockets. So there's a set of parameters where you still see the arcs in the photo emission. But if you look at quantum oscillations for this parameter, you see these oscillations very clearly. And the period of these oscillations is precisely the area of P over 8, okay, that you started with in the full pocket. Okay, so am I out of time?
Actually, you have 10 more minutes.
10 minutes.
Including the discussion.
Oh, fantastic. Okay. All right, well, I'm doing great. So that's all about the pseudogap. So to summarize, I've told you, given you this spin liquid based theory of the pseudogap. And it's really taken us 30 plus years to fully understand square lattice spin liquids. I think there's still some open questions there. And then we're now making progress on how to couple the dope these spin liquids in the right way with holes, not holons. And that, and there's a lot of support, I claim, for that approach, especially by this recent Yamaji measurement. Okay. All right, so now I want to turn to the other mysterious region of the phase diagram with the remaining few minutes. This is the strange metal. Now, unlike the pseudogap, which is very special to the cuprates, there's no other material I know that has such a large pseudogap regime where there is no known order seen. So that's really what really calls for a spin liquid based approach. So is the spin liquid somehow connected to the high TC? I believe it is, and that's another question that I won't go into. But the strange metal is very different. It's everywhere. It's seen in TBG, it's seen in the pnictides, it's seen in the nictelates, and so on. It's a much more universal phenomenology, and also, of course, in the cuprates. And of course, the famous measurement is the linear to resistivity. But I won't regard that as a signature of it because there are many explanations of linear to resistivity, including just phonons at low energies. You keep hearing models of phonons at low energies that give you linear to resistivity. Of course, that's correct. Many reasons for believing that the numbers don't work for the cuprates. But really, I want to focus on another property, which is optical conductivity. So there's a complete measurement of optical conductivity, especially in this work with Durkheim and Merrill. And from fitting the optical conductivity, they can compute what you can think of as roughly the scattering rate, or scattering time tau at each optical frequency omega. And what you find, most of these materials really, is two remarkable facts. One is that the order of magnitude, at low frequencies of tau, is just Planck's constant divided by temperature. So this is a kind of a universal value independent of any other energy scale, because only Planck's constant appears. Whether the U is 1 electron volt or 0.1 electron volt doesn't seem to matter. So that's one remarkable fact. The other fact is that even at least approximately, if you look at the frequency dependence of tau, it's scaled as omega divided by temperature. Again, no energy scale appearing. All right, and so this is the optical data showing this very cleanly. There's very subtleties in the real part of the imaginary part of conductivity that I'm not going into. And again, that took a while to sort out. All right, so is there a model for this? So we think there's a kind of a universal model that applies to the cuprates and also to other materials by an extension of the SYK model to 2 dimensions. It also applies to some version of the SYK model applies to 2-dimensional black holes, but I won't go into that, which also have Planckian dynamics. But here, let me finish with this. How do we get a model for the strange metal for the cuprates? Well, I've hopefully convinced you that the low doping metal is this FL star state. And then we have to think about how you go from FL star to the large Fermi state by some kind of quantum phase transition. Now, this is not a quantum phase transition that breaks any symmetry. The states are the same on both sides. So it has to be described by some gauge theory. And there's some Higgs field in the gauge theory whose condensation, in this case, leads to the FL star state. So this is, in some sense, a topological phase transition, although the word topological has been used in a very different sense in this conference. Nothing to do with edge states. It's a bulk transition of a gauge theory. However, what that means is that if you go superconducting, in the real world, you actually go superconducting at low temperatures. Now, if the superconducting state that descends from here and the descent from here is the same, which you believe it is, then once you're superconducting, there is no actual quantum critical point. This is just a smooth crossover. But there's a hidden quantum critical point, which unfortunately we cannot reveal, at least for the cuprates, which we are arguing is responsible. Anyway, what's going on there? Okay, I'll ignore that. All right, so you have to do a theory for this quantum phase transition. And the way you do it is you start from the large Fermi surface, you couple it to this Higgs field, but most important, it turns out, is the effect of impurities. The usual effect of impurities by a random potential, which can lead to electron localization. But here, the such effects are quite weak. But it's the randomness in the coupling, the Yukawa coupling. Lots of Japanese names in my talk. But this is what's called the Yukawa SYK model. Then it turns out to be absolutely crucial. So if you now analyze this model by SYK style techniques, it gives you these equations. And in fact, in this paper with the group of York Schmalien, we can really model both the real and imaginary part of the optical conductivity. Okay, I think I'll just end there. So what I've argued is there are two different types of critical liquids. One is this SE2 gauge theory of originally proposed by Affleck and Marston, and the other is this two-dimensional Yukawa SYK model, which are really the key ingredients in understanding the phase diagram of the cuprates. Thank you.
Yeah, thank you very much for the explanation. So now this talk is open for questions or comments. So about the synopsis transport,
Yes.
the usual hoping?
Yes. So for mercury compound, that's important. So this particular Yamaji experiment was tried in LSCO and nobody saw anything. It's only been seen for mercury, and we understand that. And the reason is that, so it's this particular compound. So in mercury, it's AA stacking of the layers.
Yeah.
So you just have a cosine dispersion.
Mm-hmm.
That's what you assume in the theoretical analysis. But for LSCO, you have one, there's a staggering of layers. And that seems to remove the Yamaji peak. You can also do calculations with that. You don't get a Yamaji peak. So it's really important that it be done in the single layer compound with AA stacking. Then you get the Yamaji effect. And that was there. This is all credit to the authors of this paper. I have nothing to do with that.
Yeah, I know Yamaji very well.
Really?
Yeah, I've been working on the layered organic superconductor.
Yes, that's right. That's why I mentioned that. And it's way back in '89.
Yeah.
But I had never heard of it until I saw this paper.
Yeah. Any other questions? Oh, please.
So once that the spin on Dirac point can strongly couple with this the pockets,
Yes.
at least then in this RPS spectrum, you see that the
Fermi arc, right?
Fermi arc
Right.
response. But yet that you claim that there is still kind of pocket remains and charge centers can provide still kind of P over A behavior. Is that the
Yes, so that was the whole point of this whole calculation. Was to show that when you couple them together, you will get the arcs. But you take the same calculation that gave you the arcs, and then you compute the oscillation, the density of states.
So this is density state. Okay.
Yes, so this is now, you have the arcs in exactly the same calculation where you have the arcs. You measure the oscillation, the density of states.
So in some sense, I cannot claim that still you have the pockets remains anymore, but still the density of state remembers this the quantization.
Yeah, so in this experiment, you are not ejecting an electron from the sample. It's still in the layer.
Okay.
In this experiment, you're ejecting it from the sample. So these are very different probes. And we're just showing, okay, here's a calculation where you can really see both effects. Now, the prediction is that this means that there should be quantum oscillations. So I'm sure people are trying. So what you need to do now is to go to, or maybe find some other material. Where did it go? Yeah, so this is done at this red point. So that's about 80 Kelvin. And that's so if you got a really, really clean system, you can work with RBCO in principle, because you're not looking at C-axis transport. That at this point, we think there should be some remnant of quantum oscillations. Yeah. Okay. I mean, this Yamaji thing was just a total surprise that this argument between arcs and pockets has been going on. But in the last few years, there's a lot of evidence for pockets, including there was work by Brad Ramshaw I didn't have time to show.
So as for the Josephson coupling around the C-axis.
I'm talking about normal states here, but yes.
Yeah. Suppose you have a superconducting.
Yes.
So then some Josephson coupling is dominated by the horon. Yeah, not the fermion.
No. So the theory of this transition here, so that was beyond this. That's also in our paper, but I didn't have time to talk about it. So I mentioned this. So now you can imagine, let's suppose you have the FL star state, and then you go into the superconductor. So that turns out to be a confinement transition. So here, this is a BCS transition. This is a confinement transition, but the states are adiabatically connected. So that's what we do so that's what we claim. But this is a confinement transition, this is a PCS transition, but in the end, it's just a PCS state. And so there's no quantum critical point. If there was really holons and spin-ons here, then this would be a true quantum critical point. But they're not present here.
I see. Yeah, question?
Thank you. So if it's diagonal, then it won't work. That's because basically the cosine is not isotopic, right?
Yeah.
At specific angles, you should have like nodes or something, maybe. So
we're just finishing a paper on exactly that.
And yeah, so
it's now done with Yahoo, and let me not say the paper will be out in a couple of weeks. I'm happy to send it to you. Just
okay, thank you.
I mean, exactly. You've been redoing all the calculations for both configurations.
Okay, let's speak again. We don't move on to the other speaker.